The telegram landed on K.T. Keller's desk at Chrysler headquarters on February 3, 1942, and the numbers on it defied rational thought. The War Production Board wanted 50,000 tanks, not over the next decade, not as some aspirational goal for American industry to work toward. They wanted 50,000 tanks as soon as humanly possible, preferably within 36 months. Keller, the bulldog-faced executive who'd clawed his way from shop floor machinist to running one of America's automotive giants, read the figure 3 times. Then he laughed out loud, a sound his secretary later described as somewhere between amusement and terror. The entire American tank inventory at that moment numbered fewer than 400 vehicles, most of them obsolete designs that wouldn't survive 10 minutes against a German Panzer. The country's combined tank production capacity, meaning every factory, every skilled worker, every machine tool currently dedicated to armored vehicle manufacturing, could produce maybe 300 tanks per month if everything worked perfectly, which it never did. Keller did the math in his head. At current rates, 50,000 tanks would take nearly 14 years. They had 3. What nobody outside Keller's inner circle knew was that he'd already been planning something that violated every principle of responsible industrial management, something his own board of directors would have called reckless if they'd understood the full scope. For the past 6 weeks, Keller had been quietly negotiating with the Army Ordnance Department, state officials, and federal regulators to implement a production system so aggressive, so fundamentally different from standard manufacturing practice, that it technically violated several wartime labor regulations before they'd even been written. His plan was elegantly simple in concept and brutally complex in execution. He would run the Chrysler tank arsenal not as a single factory, but as 3 completely independent manufacturing operations sharing the same building, 3 separate workforces, 3 separate management structures, 3 separate supply chains, all operating simultaneously, around the clock, 7 days a week, with shift changes staggered so that the production line never stopped moving. Not for lunch, not for maintenance, not for anything short of catastrophic mechanical failure or enemy bombing. The labor regulations being drafted in Washington assumed factories would operate 2 shifts with mandatory rest periods between changeovers. Keller's system would have no changeovers. Workers would literally pass tools to incoming colleagues while walking off the line. The regulations assumed standardized 40-hour work weeks with overtime caps. Keller's 3 independent operations meant workers could technically move between shifts, accumulating hours that existed in bureaucratic grey zones. The regulations assumed unified factory management reporting through single chains of command. Keller's tripartite structure created intentional ambiguity about which regulations applied to which workforce. Was it illegal? The lawyers couldn't say definitively because the laws hadn't caught up with the emergency. Was it ethical? That depended entirely on whether you valued the lives that faster production might save over the exploitation of workers who'd signed up for patriotic sacrifice and got industrial machinery instead. Keller didn't lose sleep over the question. He'd lost sleep over Bataan. He'd lost sleep over the reports from North Africa where American tankers were dying in Shermans that arrived months too late. The moral mathematics were clear to him. Every day of accelerated production was a day closer to ending the dying. Everything else was accounting. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The Warren Tank Arsenal, which would eventually become the most productive tank factory in human history, started as a muddy field outside Detroit in the summer of 1940. The groundbreaking ceremony on September 9th featured politicians making speeches about American resolve, while photographers captured images for newspapers. What the cameras didn't show was the army of surveyors working frantically behind the ceremonial tent, recalculating building dimensions because the original plans had underestimated the space required for tank assembly by nearly 40%. The construction timeline bordered on the physically impossible. Chrysler had promised a functioning factory within 12 months, but that assumed sequential construction. Foundation first, then walls, then roof, then utilities, then equipment installation, then worker training, then trial production, traditional factory construction. Keller threw out traditional on his first site visit. He ordered construction and production preparation to proceed simultaneously. While concrete was still curing on the eastern wing, machine tools were being installed in the western section. While electricians wired the southern assembly area, welders were practicing on scrap metal in the northern training facility. The factory was being built around workers who were already learning to use it. The numbers involved stagger comprehension. The main building covered 710 acres under a single roof, making it the largest manufacturing facility in the world at that time. The roof alone required enough steel to build 2,000 automobiles. The electrical system could power a city of 50,000 people. The heating system burned enough natural gas daily to heat 12,000 homes through a Michigan winter. And all of this infrastructure existed for one purpose only: converting raw steel into mobile armored warfare at a pace the world had never witnessed. The first M3 Lee tanks rolled off the Warren Line in April 1942, just 19 months after that muddy groundbreaking. The production rate was pathetic by later standards. 8 tanks per day, 60 per week, each one essentially hand-built by workers still learning their trades. The reject rate was nearly 15%, meaning 1 in 7 tanks failed Army acceptance tests and had to be rebuilt. Quality control officers found cracked welds, misaligned components, improperly torqued bolts, and a dozen other defects that would have been unacceptable in peacetime manufacturing. But Keller wasn't measuring success by quality metrics alone. He was measuring it by learning curves. Every defect caught was a defect understood. Every worker who made a mistake and corrected it was a worker who wouldn't make that mistake again. Every failed tank was a classroom. He ordered his supervisors to document everything. Every flaw, every near miss, every moment where a worker hesitated because the instructions were unclear. These reports, thousands of pages accumulating weekly, became the raw material for relentless process improvement. The breakthrough came not from engineering genius, but from a stamping press operator named Harold Wikstra, who'd spent 20 years making Chrysler fenders before the war. Wikstra watched the tank hull assembly process for 3 weeks during his breaks, saying nothing, just observing. Then he submitted a suggestion through the factory's idea box, a system Keller had borrowed from pre-war automotive manufacturing. His suggestion was deceptively simple: move the hull welding stations from a linear configuration to a circular arrangement, allowing welders to work on multiple seams simultaneously instead of waiting for sequential access. The engineering department initially rejected the idea. Circular configurations created material handling complications. Forklifts would have trouble navigating. The overhead cranes would need repositioning. Too complex, too risky, not worth disrupting a line that was finally achieving consistent output. Wikstra didn't argue. He simply built a scale model during his lunch hours using cardboard, string, and bottle caps to represent workers and equipment. He presented it to his shift supervisor, who happened to mention it to Keller during a walkthrough. Keller studied the model for 20 minutes. Then he ordered immediate implementation on the night shift line, giving the engineers exactly 48 hours to figure out the crane problem. They did. What had taken a team of welders 4 hours of sequential work now took 90 minutes of parallel effort. Hull production jumped 40% overnight. Wikstra received a $50 bonus, and his suggestion was distributed to every tank factory in America. Within 6 months, circular welding stations became standard across the industry, and Harold Wikstra went back to his stamping press, content that he'd done his part. The transformation of ordinary Americans into tank builders happened with shocking speed because Keller understood something the traditional defense contractors didn't. You don't train people to be experts. You redesign the work so expertise becomes unnecessary. This wasn't a new concept. Henry Ford had proven it decades earlier with automobile assembly. But applying it to military hardware required overcoming institutional resistance from an Army Ordnance Department that believed weapons required craftsmen, not production workers. The training system Keller implemented was based on ruthless task decomposition. A Sherman tank contained over 8,000 individual components, but no single worker needed to understand all of them. Instead, each position on the assembly line was broken into discrete tasks that could be mastered in days rather than years. A worker installing transmission mounts needed to know exactly three things: how to read the torque wrench, how to verify the mount alignment using a simple gauge, how to recognize the 5 most common defects that required supervisor attention. That was it. Nothing about how transmissions worked. Nothing about why the torque specification mattered metallurgically. Nothing about the tank's overall design philosophy. Just those 3 skills, repeated hundreds of times per shift until they became automatic. Critics called it dehumanizing. Workers weren't learning a trade. They were becoming biological components in a vast machine, their humanity subordinated to production efficiency. The critics weren't entirely wrong. Night shift workers reported dreams where they were stuck in endless loops, performing the same motion repeatedly, unable to stop even in sleep. Repetitive strain injuries skyrocketed. The factory clinic treated more than 300 cases of tendinitis in the first year alone. Workers' hands would seize into claws after 8-hour shifts of identical gripping motions. The spring of 1943 brought a crisis that almost derailed the production miracle entirely. The Continental R-975 engine supply collapsed when the Muskegon plant experienced a catastrophic fire that destroyed 3 assembly lines and killed 6 workers. The engines that Warren depended upon simply stopped arriving. The factory had maintained a 2-week buffer stock precisely for such emergencies, but nobody had anticipated a disruption that would last months rather than days. Keller's response demonstrated the adaptive flexibility that made Warren different from traditional manufacturing. Rather than shut down production and wait for Continental to rebuild, he authorized a radical modification. Warren would accept alternative engines, specifically the Chrysler A57 multibank engine, a bizarre power plant created by bolting 5 automobile engines together on a common crankcase. The A57 was heavier, less reliable, more maintenance-intensive, and consumed more fuel. Army Ordnance hated it. Tank crews would hate it even more, but it was available immediately from Chrysler's Detroit facilities. The production line had to be reconfigured in 72 hours to accommodate the different engine mounting requirements. Workers who'd mastered Continental installation had to relearn procedures for the A57. The testing protocols had to be rewritten. The supply chain had to pivot. The chaos was controlled, but barely. Production dropped 40% that first week as workers adapted. But it didn't stop completely. Tanks kept rolling, just slower and with different hearts. By the time Continental returned to full capacity 3 months later, Warren had produced over 1,000 Shermans with the A57 engine. They weren't the preferred variant, but they were tanks on battlefields where any tank was better than no tank. But the production numbers told a different story. By September 1942, Warren was producing 18 tanks per day. By December, 26. By March 1943, the line was averaging 35 Sherman tanks every 24 hours, more than the entire American tank output for all of 1940. Workers who'd never seen a tank before January were now producing them at rates that made German industrial planners question their intelligence reports. Surely these numbers were American propaganda. They weren't. The workforce composition itself became a secret weapon. By mid-1942, roughly 35% of Warren's assembly line workers were women, a percentage that would eventually climb past 40%. These weren't just replacements for drafted men. Statistical analysis later showed that female workers in certain precision tasks actually outperformed their male counterparts, particularly in electrical wiring and instrument calibration, where smaller hands and greater fine motor control provided advantages. Dorothy Patterson, a former telephone switchboard operator, became famous on the floor for wiring turret electrical systems in half the standard time with 0 defects over a 6-month period. Her technique was studied and documented, becoming the standard training protocol. The tooling crisis of early 1942 nearly ended the production miracle before it began. Precision machine tools, the equipment that makes equipment, were in desperately short supply across America. Every defense contractor was screaming for lathes, milling machines, grinding equipment, and specialized jigs. The machine tool industry couldn't scale fast enough. Machines that took 6 months to build in peacetime were being demanded in weeks. Warren's initial production targets assumed tool availability that simply didn't exist. Keller's solution was simultaneously brilliant and terrifying. He ordered his engineers to redesign tank components specifically to work with available tools, rather than optimal tools. The turret traverse mechanism, originally designed for precision gear cutting that required specialized equipment, was redesigned to use standard automotive gear cutting machines that Chrysler already owned. The redesign wasn't as elegant. The traverse action was slightly rougher, but it worked, and more importantly, it could be produced immediately using existing capacity. Similar compromises rippled through the entire tank design. Each compromise traded some degree of mechanical perfection for production reality. The factory also employed workers that other defense plants rejected. Men with physical disabilities found positions where their specific limitations didn't matter. A worker, missing 3 fingers on his left hand, excelled at a station requiring only right-hand manipulation. Legally blind workers operated stations that relied on tactile feedback rather than visual inspection. Deaf workers thrived in the deafening environment of the stamping area, where hearing was actually a liability because the noise was so overwhelming. Keller didn't make these accommodations from some enlightened social consciousness. He made them because he needed bodies on the line, and discovered that so-called limitations often created unexpected advantages when tasks were properly designed. The night shift developed its own subculture that fascinated industrial sociologists who studied the factory decades later. Working when the world slept created bonds between workers that transcended normal workplace relationships. Night shifters married each other at rates far exceeding statistical expectations because they were the only people who understood the inverted life. Their children grew up in households where breakfast happened at dinner time and bedtime was dawn. The night shift workers developed their own slang, their own jokes, their own way of seeing the factory that day shifters couldn't quite understand. They called themselves the Shadow Army, building weapons in darkness while America slept. The cafeteria served over 15,000 meals daily across all 3 shifts, making it one of the largest food service operations in Michigan. The menu was designed by nutritionists who understood that industrial workers needed sustained energy, not quick bursts. High protein, complex carbohydrates, minimal sugar. Coffee flowed continuously from urns that were never allowed to empty. Workers developed rituals around their breaks. The 15-minute meal periods became precisely choreographed. Workers knew exactly how long it took to reach the cafeteria, how long to eat, how long to return. Wasted time was production lost. The continuous operations system that made Warren different from every other factory in America was built on overlapping 8-hour shifts that never fully separated. Traditional factories stopped between shifts. Machines powered down. Workers departed. New workers arrived. Machines restarted. This transition period, usually lasting 30 to 60 minutes, meant dead time when nothing was produced. Keller eliminated it completely through a system he called rolling transition. Here's how it worked. The Warren workforce was divided into 3 completely separate organizations, each with its own management, its own training programs, its own supply chains, and its own identity. Workers referred to themselves as first shifters, second shifters, or night shifters, as if they worked for different companies. Each shift had distinct uniforms, colored badges, and even separate cafeteria times. This separation was intentional because it created competition between shifts. Which shift could produce more tanks with fewer defects? The rivalry became intense, with bragging rights celebrated like sports victories. When shifts changed, workers didn't wait for lines to stop. Incoming workers shadowed outgoing workers for 30 minutes before the official changeover. At the exact transition moment, the outgoing worker would step aside, while the incoming worker stepped forward, and the tank on the line wouldn't know the difference. The torch passed without pausing. Tools transferred hand to hand. The outgoing worker would give a 30-second verbal briefing. This is where I am on the weld. Watch the third seam because the metal is running hot. Check the alignment on the next hull because number 7 crane has been drifting left. Then gone, replaced by fresh hands continuing the exact same motion. The psychological effect on workers was profound and not entirely healthy. Sleep patterns were destroyed because biological clocks can't adjust to artificial shift rotation. First shift ran 6 a.m. to 2 p.m. Second shift 2 p.m. to 10 p.m. Night shift 10 p.m. to 6 a.m. Workers on rotating schedules never fully adapted. The factory ran continuously, but human circadian rhythms didn't care about war production schedules. Absenteeism on night shift was consistently 12% higher than day shift. Quality defects on night shift were 14% higher. Accident rates were nearly double. Keller's solution was characteristically pragmatic and ruthless. He stopped rotating workers between shifts. Once assigned to night shift, you stayed on night shift permanently unless medically disqualified. This meant some workers essentially lived in perpetual darkness, seeing sunlight only on their days off. Their families adjusted to reversed schedules, marriages strained under the unnatural rhythms. But production stabilized because workers' bodies eventually adapted to consistent schedules, even if those schedules violated every biological norm. Night shift became a tribe unto itself, bonded by shared sacrifice and the strange brotherhood of perpetual darkness. The material flow system that fed the never-stopping line was an engineering marvel that's rarely discussed in histories of wartime production. Every single component arriving at Warren had to reach the line at exactly the right moment. Too early meant storage costs and potential damage. Too late meant line stoppage, the ultimate sin in continuous production. Managing this for one shift would be challenging. Managing it for 3 independent shifts operating continuously was logistical choreography of staggering complexity. Chrysler's logistics team developed what they called the cascade system. Supplies didn't arrive at the factory as needed. They arrived at feeder warehouses positioned around the main facility. Each warehouse specialized for specific component types. Steel plates went to Warehouse 1, electrical components to Warehouse 2, engines from Continental to Warehouse 3. Each warehouse then fed the main line based on real-time consumption signals sent via pneumatic tubes from the assembly floor. When a station consumed a component, a signal was sent. The warehouse had exactly 17 minutes to deliver replacement stock before the buffer ran out. Miss that window, and the line stopped. Nobody wanted to be the person who stopped the line. The supplier network extended across 23 states, with over 500 companies providing components that all had to arrive at Warren with perfect coordination. Continental Aircraft Engine in Muskegon, Michigan, supplied the R-975 radial engines. American Locomotive in Schenectady, New York, provided hulls that Warren would complete. Firestone in Akron, Ohio, delivered the rubber track components. Pittsburgh Steel supplied armor plate. Every supplier was given production schedules matching Warren's impossible pace, and those who couldn't keep up were replaced immediately. There was no negotiation, no second chances. The line couldn't stop, which meant the supply chain couldn't falter. The railway system serving Warren became a dedicated military logistics operation. 4 rail lines converged on the facility, with trains arriving around the clock. Empty cars were removed immediately to make room for arriving freight. Switching operations ran continuously, orchestrated by a control tower that looked more like an air traffic control facility than a rail yard. Dispatchers tracked every incoming car, knew its contents, its destination warehouse, its unloading schedule. A single train running late could cascade through the entire system, potentially threatening production, so trains weren't allowed to run late. The railroad prioritized Warren shipments above all other freight, and delays were investigated with the intensity normally reserved for criminal matters. The steel alone presented logistical nightmares that would have paralyzed lesser organizations. Each Sherman tank required approximately 33 tons of finished steel, though the actual steel consumed in production was closer to 45 tons when accounting for machining waste, quality rejects, and processing losses. Warren consumed roughly 10,000 tons of steel daily at peak production. That's 10,000 tons arriving by rail, being unloaded, sorted, distributed to proper stations, and converted into armoured vehicles before the next 10,000 tons arrived the following day. The steel mills in Pittsburgh and Gary operated 3 shifts specifically to maintain Warren's appetite. When a rolling mill broke down in Bethlehem in July 1943, the ripples threatened to reach Warren's line within 72 hours. Emergency repairs ran around the clock. The mill was back online in 61 hours. Nobody wanted to be the supplier who stopped Warren. The quality control system evolved into something that resembled military intelligence operations more than industrial inspection. Every tank received a unique serial number stamped into 12 different locations throughout the vehicle. This wasn't bureaucratic redundancy. It was traceability. If a tank failed in combat due to a manufacturing defect, investigators could trace that specific vehicle back through the production system to identify which worker on which shift at which station had touched that component. The knowledge that your work was permanently traceable focused attention in ways that supervisory oversight never could. Workers knew that their name was essentially welded into every tank they touched. That connection between action and consequence proved more effective than any punishment system. Statistical quality control was implemented at Warren before most American manufacturers had heard the term doctor. Walter Schuhart's control chart methods, developed at Bell Laboratories in the 1920s, were applied rigorously to tank production. Every measurable parameter, from weld penetration depth to bore concentricity, was tracked on control charts. Workers learned to read these charts, understanding that a process drifting toward control limits required correction before defects occurred. The system caught problems while they were still variations, not failures. A weld that was approaching inadequate penetration depth could be corrected by adjusting torch angle or travel speed. No defective product was created. The statistical thinking transformed workers from reactive troubleshooters into proactive process controllers. The testing grounds adjacent to the factory became legendarily brutal. Every single tank, before receiving Army acceptance, had to complete what workers called the torture track. 3 miles of deliberately punishing terrain designed to stress every component beyond normal operational limits. Tanks climbed grades that exceeded anything they'd face in European terrain. They descended slopes so steep that brake systems were tested to failure margins. They crossed water obstacles that submerged hulls up to turret level, testing waterproofing seals under actual immersion. They fired main guns while moving over rough terrain, testing stabilization systems under combat representative conditions. The failure rate on the torture track was initially horrifying. Nearly 18% of tanks failed some portion of the acceptance test in early 1942. Transmissions that couldn't handle the sustained climbing, electrical systems that shorted during water crossing, tracks that threw themselves off bogie wheels under lateral stress. Each failure was an education. Engineers analyzed the failure modes, redesigned vulnerable components, updated production specifications, and the fixes propagated through the system. By mid-43, the failure rate had dropped to just over 4%, and most of those failures were minor issues correctable in hours rather than days. The sound of Warren production became its own signature. Visitors described it as unlike any factory they'd encountered. Traditional automotive plants had rhythmic sounds, predictable cycles of stamping presses and assembly operations, creating an industrial heartbeat. Warren's sound was more chaotic, a symphony of overlapping operations running continuously without the punctuation of shift changes or break periods. The welding areas crackled with constant electrical discharge. The engine testing bays roared with radial engines running at full throttle. The metal forming areas rang with the percussion of shaping operations. The final assembly areas hummed with the more subtle sounds of precision work, all of it blending into a continuous industrial roar that workers claimed they could hear in their sleep for years after the war ended. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. September 17, 1943 became the day that rewrote industrial history. It was a Wednesday, though nobody working at Warren that day would remember the day of the week. What they remembered was the number that appeared on the production board at 6 a.m. Thursday morning, 284. That was the number of completed Sherman tanks that had rolled off the Warren line in the preceding 24-hour period. 284 tanks, not components, not partially assembled hulls, complete, tested, combat-ready armoured fighting vehicles, each one weighing 33 tons, each one containing over 8,000 individual parts, each one capable of carrying a crew of 5 into battle against German armour. The mathematics of that achievement still astonish. 284 tanks in 24 hours means 11.83 tanks per hour. That means one complete tank every 5 minutes and 4 seconds. While you eat a sandwich, a tank is finished. While you walk from your car to your house, a tank is finished. While you're brushing your teeth, a tank is finished. The factory was producing armoured warfare machines with the casual regularity of a baker producing loaves of bread. To comprehend what this meant in practical terms, consider that Germany's entire monthly Panther production in 1943 averaged roughly 300 vehicles. Warren matched that in a single day, and the Panther was supposed to be Germany's answer to Allied armour superiority. The Germans were allocating their finest engineers, their most skilled craftsmen, their most advanced materials, and their most sophisticated manufacturing techniques to produce 300 Panthers monthly. Warren was producing the same number of tanks using workers who'd been bank tellers and housewives a year earlier, using assembly line techniques borrowed from automobile manufacturing, using designs that prioritized production simplicity over engineering perfection. The secret to the September record wasn't any single innovation. It was the cumulative effect of thousands of small improvements that had been implemented over the preceding 18 months. Each suggestion box idea that shaved 30 seconds off a process, each worker who discovered a slightly better tool grip, each supervisor who noticed a bottleneck and rerouted workflow, each maintenance worker who preemptively replaced a component before it failed, each quality inspector who caught a defect pattern and traced it to root cause. None of these improvements would merit mention in an engineering textbook, but compounded across thousands of workers over thousands of shifts, they created a production capability that shouldn't have been possible according to any industrial engineering manual of that era. The workforce that achieved this record had evolved into something unprecedented in industrial history. They weren't skilled craftsmen in the traditional sense. They couldn't explain the metallurgical properties of armor plate or the thermodynamic principles governing engine performance. But they had developed a different kind of expertise. They could feel when something was wrong before instruments detected it. Veteran workers claimed they could hear defects, a weld that didn't sound quite right, an engine that had a barely perceptible vibration, a transmission that shifted with microseconds of delay. These intuitions, developed through thousands of hours of repetitive work, caught problems that formal quality control missed. Margaret O'Sullivan worked Station 47, installing fuel line connections. She'd been a dressmaker before the war, and her nimble fingers proved perfect for the delicate work of securing brass fittings without over-torquing them. By September 43, she'd installed fuel connections on over 12,000 tanks. Her hands knew the exact amount of pressure required. Too tight, and the brass would deform, creating potential leak points. Too loose and fuel would seep, creating fire hazards. The specification called for 23 foot-pounds of torque. Margaret didn't use a torque wrench anymore. Her hands had become the instrument, accurate to within half a foot-pound based on feel alone. Quality control stopped checking her work after the first 6 months because she'd never once failed an inspection. The engine installation process became a study in synchronized precision that visitors found almost hypnotic to watch. The Continental R 975 radial engine weighed over 1,100 pounds. Getting it into the tank's engine bay required overhead cranes, positioning jigs, and 4 workers moving in perfect coordination. The margin for error was less than half an inch. Drop the engine wrong and you'd damage the mounting points, requiring hours of rework. Position it slightly off-center and the driveshaft wouldn't align with the transmission. The 4-person team at Station 92 had performed this operation so many times that they'd developed an almost telepathic coordination. They communicated through hand signals and barely perceptible nods. Their installation time dropped from 45 minutes in early production to just 11 minutes by peak efficiency. They'd become a single organism with 8 arms, all devoted to one purpose. Frank Morrison worked the engine testing station, the last stop before tanks left the line. His job was to listen to each Continental radial engine during its initial run-up, checking for any anomaly in the characteristic sound of a properly functioning power plant. Frank had been a piano tuner before the war, his ears trained to detect minute pitch variations. He claimed he could identify 18 different engine problems just by sound. A valve running slightly hot had a different tone than a valve running cool. A misaligned piston created a rhythmic variation that was almost subliminal. Frank's rejection rate was higher than other testers, which initially concerned supervisors. But follow-up analysis showed that tanks Frank rejected and fixed had 0 field failures related to engine problems. Those he approved ran without issues. His ears were more accurate than any diagnostic equipment available at the time. The paint department operated under pressure that other stations couldn't comprehend. Every tank required over 40 gallons of olive drab paint applied in multiple coats. The paint had to adhere properly to prevent corrosion in salt air environments. It had to dry quickly, enough to not slow the line. It had to be thick enough for protection, but not so thick that it added unnecessary weight or clogged small openings. The paint formulation was adjusted seasonally because temperature and humidity affected drying times. Winter paint had different solvent ratios than summer paint. Workers in the paint booths wore respirators and protective clothing that made them look like space explorers. Their exposure limits were strictly enforced because the solvents were brutally toxic. Shift rotations in the paint department were shorter than other areas, with workers spending only 4 hours in booths before rotating to less hazardous stations. The ammunition storage area installation became critically important after reports from North Africa described Sherman tanks detonating catastrophically when hit. Early Sherman design stored ammunition vertically along the hull sides, convenient for loaders but catastrophic when penetrated. A single armor-piercing round could strike the ammunition rack, and the resulting explosion would be instant and total. Crews called the Shermans Ronsons after the cigarette lighter company, whose slogan promised they'd light on the first strike. The nickname wasn't affectionate. Warren implemented wet ammunition storage as soon as the redesigned specifications arrived from Army Ordnance. The new system placed ammunition in protected bins, surrounded by water jackets filled with a mixture of water and glycerin that wouldn't freeze. If a round penetrated the hull, the water would absorb heat and suppress any fire before it could reach the propellant charges in the shells. The modification added weight and reduced total ammunition capacity, but it saved lives. Tanks with wet stowage had survival rates nearly 25% higher than those without. The workers installing these systems understood the direct connection between their labor and crew survival. The quality metrics on wet stowage installation were perfect. Nobody wanted to be responsible for a crew burning to death because a water jacket leaked. The September record production wasn't repeated immediately because it had pushed the system to absolute limits and revealed stress points that needed addressing. Several machine tools required emergency maintenance after running beyond designed duty cycles. 2 overhead cranes needed bearing replacements that should have happened weeks earlier, but had been postponed to maintain production. Worker injury rates spiked noticeably as fatigue accumulated. The factory had proven what was possible. Now it had to figure out what was sustainable. The answer came from an unexpected source. Dr. William Menninger, a psychiatrist working with the Army on combat stress, visited Warren in October 1943 to study production worker psychology. What he found both disturbed and fascinated him. Workers were experiencing stress symptoms remarkably similar to combat troops. Hypervigilance about quality, defects. Nightmares about tanks failing in battle. Overwhelming responsibility for distant soldiers' lives. Guilt when production targets were missed. Pride that bordered on identity fusion with the tanks they built. Menninger's recommendation was counterintuitive. Instead of reducing the pressure, he suggested amplifying the connection between workers and combat outcomes. His theory was that abstract stress was more damaging than concrete stress. Workers were anxious about faceless soldiers in distant battles. Make the soldiers real, and the anxiety would transform into purposeful motivation. Keller implemented the suggestion immediately. Letters from tank crews started appearing on bulletin boards. Photographs of Sherman tanks in combat were posted throughout the factory. When possible, soldiers on leave visited the plant, shaking hands with the workers who'd built their tanks. The effect was profound and immediate. One letter in particular circulated through the factory like scripture. Sergeant Thomas Wheeler from the 2nd Armored Division wrote, describing how his tank, which he'd named Detroit Steel after learning it came from Warren, had taken a direct hit from a German 88mm gun. The round penetrated the frontal armor, but the internal fire suppression system, a recent addition to the production line, prevented ammunition detonation. His crew survived with minor injuries. Wheeler closed his letter with words that workers repeated to each other during difficult shifts. The weld that saved my life was probably made by someone whose name I'll never know, but I think about that person every day. Whoever you are, thank you. You gave me Christmas with my family. After the September record, Warren settled into a production rhythm that balanced maximum output with sustainable operations. The daily average stabilized around 220 tanks, which meant roughly 9 tanks per hour, or 1 tank every 6.5 minutes. Still, an absolutely staggering achievement, but achievable without destroying the workforce or the machinery. This rate held remarkably steady through the remainder of 43 and into 44, creating the industrial foundation that made D-Day possible. The stockpile of Sherman tanks that accumulated in England before the Normandy invasion existed only because Warren and the other American tank factories had created an unprecedented surplus. By June 6, 1944, American forces had access to more operational tanks than they had trained crews to operate them. This wasn't a minor surplus. Entire tank battalions could be completely re-equipped after suffering catastrophic losses, and they frequently were. The Germans couldn't understand how American armoured strength seemed to regenerate after battles that should have crippled entire divisions. The Battle of the Bulge in December 1944 provided the ultimate test of Warren's production philosophy against German engineering excellence. German forces committed their remaining Panther and Tiger reserves in a desperate offensive through the Ardennes. Initial German successes seemed to validate their quality over quantity approach. American Sherman units were mauled in the early engagements, with Panthers destroying Shermans at ratios that horrified Allied commanders. Individual German tanks accumulated dozens of kill markings, while American units reported 80% casualties. But the Germans couldn't sustain their success because they couldn't sustain their losses. A Panther requiring transmission replacement sat immobilized for weeks because spare parts had to be manufactured individually. A Sherman needing the same repair was back in action within days because standardized parts arrived on predictable supply schedules. German units that started the offensive with full strength found themselves at half strength within 2 weeks. Not from combat losses alone, but from mechanical failures they couldn't repair. American units starting at half strength from combat losses were back to full strength within the same time frame because replacement tanks arrived from depots stocked by Warren's production. The mathematics became brutal and irrefutable. Germany lost the Battle of the Bulge not on the battlefield, but in the factories. They couldn't replace their losses. America could. The Shermans that Keller's system produced in seemingly infinite quantities proved the difference between an offensive that stalled and one that succeeded. German commanders later admitted they'd been fighting the wrong war entirely. They'd been optimizing for tank duels. The Americans had optimized for industrial warfare. The Americans won. The answer was simple mathematics that German industrial planners refused to accept as possible. America was producing tanks at ratios that seemed fictional. For every German tank built, America was building 15, not because American workers were superior, not because American technology was more advanced, not because American resources were more abundant, though they certainly were. The difference was philosophical. Germany built tanks as if they were works of military art, each one a masterpiece of engineering requiring skilled craftsmen. America built tanks as if they were industrial products, each one a standardized unit emerging from an optimized system. The philosophy that seemed crude and unsophisticated to German engineers turned out to be the philosophy that won wars. The post-war fate of the Warren facility itself reflected the broader story of American industrial adaptability. The massive complex that had produced tanks with such remarkable efficiency was converted back to automotive production almost as quickly as it had been converted to military manufacturing. The same assembly lines that rolled out Shermans began rolling out civilian vehicles. The overhead cranes that had lifted tank turrets now lifted automobile bodies. The testing grounds that had tortured tanks became proving areas for new car models. The transition was so smooth that it almost seemed to mock the immense difficulty of the original conversion. But that smoothness was itself a product of the systems thinking that Keller had implemented. The human cost of this achievement was substantial and largely invisible in official histories. Warren's medical clinic treated an average of 240 workers per shift for various injuries and ailments. Repetitive stress injuries were endemic. Hearing loss from constant industrial noise was universal. Chemical exposure from welding fumes, paint solvents, and hydraulic fluids caused respiratory issues that workers wouldn't fully understand for decades. The occupational health standards that exist today were unknown then, and the urgency of war production meant that long-term health considerations were subordinated to immediate output needs. The social transformations were equally profound. Families reorganized around factory schedules. Children adapted to parents who were present but exhausted. Communities formed around shift schedules rather than neighborhoods. Churches held separate services for different shifts. Businesses adjusted hours to serve workers operating on war production time. The region around Warren transformed from a rural Michigan farming community into an industrial complex, rivaling any urban manufacturing center. The tanks Warren produced didn't just fight in Europe. They fought across the Pacific, though that story is less commonly told. Marine tankers on Iwo Jima drove Warren-built Shermans through volcanic ash so fine it clogged air filters and jammed turret mechanisms. The tanks weren't designed for that environment, but they adapted because the crews adapted. Field modifications became routine. Warren engineers received feedback from Pacific operations and incorporated lessons into production specifications. The final Shermans rolling off the line in mid-1945 included improvements specifically designed for conditions that early production models had never been tested against. The Okinawa campaign in spring 1945 consumed Shermans at rates that would have been impossible to sustain without American production capacity. Japanese defensive positions, dug deep into coral ridges and protected by interlocking fields of fire, required armor to approach infantry strongpoints. Tanks were destroyed daily by suicide attacks, mines, and concentrated artillery. The 3rd Armored Amphibian Battalion lost every single one of its Sherman tanks at least once during the campaign, some tanks being destroyed and replaced multiple times. Only Warren's production miracle made this attrition sustainable. Fresh tanks arrived on supply ships with predictable regularity, crewed by replacements trained on equipment identical to what they'd operate in combat. The logistical system that connected Detroit assembly lines to Pacific Island beaches stretched 12,000 miles, but functioned with remarkable reliability. When the war ended in August 1945, Warren's production lines didn't immediately stop. There was existing inventory to complete, contracts to fulfill, and a gradual wind-down process that took months rather than days. Workers who'd spent years in the hypnotic rhythm of tank production found the transition to peacetime manufacturing jarring. the intensity, the purpose, the daily awareness of building something that mattered in the most profound way possible, all of that evaporated. Post-war Chrysler manufacturing, while still demanding, felt hollow to many workers. They'd built machines that saved lives and won battles. How do you go back to building car fenders after that? The final production tally from Warren specifically was 22,134. Sherman tanks produced from April 1942 to August 1945. That's a little over 21% of all Sherman tanks manufactured. Combined with other Chrysler facilities, the company produced over 25,000 tanks during the war. The numbers are almost too large to comprehend. Imagine 22,000 tanks lined up track to track. That line would stretch over 200 miles. Warren produced an armoured formation larger than any field commander had ever deployed, and they did it from a single factory using workers who'd learned their trades in less time than it takes to get a college degree. The German High Command received intelligence reports about American production rates that they simply refused to believe. General Heinz Guderian, Germany's foremost armoured warfare expert, read the figures in early 1944 and declared them obvious Allied propaganda. American factories producing 300 tanks daily? Impossible. The Americans were clearly exaggerating to intimidate. German intelligence. Officers revised the numbers downward to what they considered realistic levels, roughly one-third of actual production. This miscalculation would prove fatal to German strategic planning. The reality that German planners couldn't accept was that American industrial philosophy fundamentally differed from German manufacturing tradition. German industry valued craftsmanship. Each Panther tank was essentially hand-built by skilled workers who understood every component. German tank crews had personal relationships with the workers who built their vehicles. This relationship created quality but strangled quantity. A German tank factory might produce 50 Panthers monthly using workers who'd trained for years. Warren produced 50 Shermans in 12 hours using workers who'd trained for weeks. The mathematics were irreconcilable. K.T. Keller received relatively little recognition for his achievement. He returned to running Chrysler, applying lessons from wartime production to peacetime automobile manufacturing. The techniques he'd pioneered, continuous production, task decomposition, rolling shift changes, supply chain optimization, these concepts filtered into general industrial practice without much acknowledgement of their wartime origins. Business school textbooks would eventually teach these methods as generic best practices, without noting that they'd been invented under the desperate pressure of global war. The Soviets learned from Warren's example more deliberately than Western manufacturers. Soviet industrial planners visited American factories during the war under the Lend-Lease program. What they saw at Warren fascinated them. The continuous production model, the task decomposition, the statistical quality control, all of it was studied and documented. When the Cold War began, Soviet military production adopted many Warren innovations while claiming them as Soviet inventions. The Ural tank factory in Nizhny Tagil eventually implemented continuous production, methods that Soviet engineers privately acknowledged were borrowed from American wartime manufacturing. The student had become the competitor. The workers themselves scattered back into peacetime anonymity. Margaret O'Sullivan returned to dressmaking, but found her hands had lost the delicate touch after years of working with industrial fittings. Frank Morrison went back to piano tuning, but admitted that engines sounded more interesting to him now than strings. Harold Wickstra remained at Chrysler, eventually becoming a shop floor supervisor, though he never again submitted a suggestion that had such immediate impact. The circular welding stations he'd envisioned are still used in modern manufacturing, though nobody remembers the stamping press operator who first sketched them with cardboard and bottle caps. Dorothy Patterson, the telephone operator turned turret electrician, tried to explain her wartime work to her children decades later. She showed them photographs of the massive factory, tried to describe the sound of 3 shifts working continuously, attempted to convey the weight of responsibility they all felt. Her children nodded politely but couldn't quite understand. How could they? They'd grown up in peacetime prosperity, partly enabled by their mother's wartime labor, but had no framework for understanding what that labor meant. The tanks their mother had wired were rusting in military museums now, historical artifacts rather than living weapons. The Warren tank arsenal itself became the Detroit Arsenal tank plant and continued military vehicle production through the Cold War. The same facility that produced Shermans would produce M48 Patton tanks in the 1950s, then M60 tanks in the 60s. The production methods Keller had pioneered remained the foundation, though technology advanced. Computer-controlled machines replaced some manual operations. Automated welding supplemented human welders. Quality control systems used sensors and data analysis rather than just human observation. But the core philosophy remained unchanged. Break complex products into simple operations. Train workers on specific tasks rather than comprehensive skills. Maintain continuous flow rather than batch production. Standardize everything possible to enable replacement and logistics. The Sherman production innovations had become manufacturing orthodoxy. The legacy of Warren's achievement extends far beyond military history. The factory demonstrated that with proper systems design, ordinary people could accomplish extraordinary things. The workers weren't exceptional individuals selected for their talents. They were randomly assembled from the general population, trained in weeks rather than years, and asked to produce sophisticated military hardware at rates that defied industrial logic. And they succeeded beyond any reasonable expectation. Modern manufacturing owes more to Warren than most practitioners realize. The just-in-time supply chains that dominate global production were pioneered in Warren's feeder warehouse system. The continuous improvement methodologies that Japanese manufacturers would later formalize as Kaizen were happening informally on Warren's production floor through the suggestion box system. The cross-training protocols that modern factories use to build workforce resilience were developed out of necessity when Warren's 3 independent shifts needed workers who could cover multiple stations. The concepts seem obvious now. They weren't obvious then. They were invented by people solving immediate problems under tremendous pressure, and those solutions became the foundation for how we build things today. Perhaps the most profound legacy was proving that quantity, properly organized, becomes its own quality. German tank commanders consistently reported frustration that they could win every engagement and still lose the campaign. Their Tigers and Panthers were technically superior to Shermans in most measurable ways: better armor, better guns, better optics, better crew training. In single combat, a Panther would defeat a Sherman more often than not. But war isn't single combat. War is attrition and logistics, and the cold mathematics of replacement rates. A Panther that destroyed 3 Shermans in battle was still a loss for Germany if the Americans simply replaced those 3 while the Panther sat immobilized waiting for spare parts that would never arrive. The moral questions surrounding Warren's achievement don't have comfortable answers even decades later. Was it ethical to push workers to physical and psychological limits that caused lasting damage? The injury rates, the repetitive stress disorders, the hearing loss, the chemical exposures, none of these were hidden from workers. They knew the risks and accepted them as patriotic duty. But did they truly understand the long-term consequences? Could they have understood when the immediate crisis of global war demanded their sacrifice? Veterans of Warren's production lines carried their experiences differently. Some spoke with pride that bordered on reverence. They'd been part of something larger than themselves, something that mattered in the most fundamental way. Their work had saved lives, shortened the war, helped defeat genuine evil. That meaning sustained them through decades of peacetime work that felt trivial by comparison. Others carried bitterness. They'd sacrificed their health, their family time, their youth for wages that seemed inadequate and recognition that never came. The government used them and discarded them. The companies made profits while workers made injuries. Both perspectives contained truth. Warren embodied this philosophy completely. The factory didn't produce the best tank, it produced enough tanks, and in total war, enough is what matters. The men crewing those Shermans understood this bargain, even if they didn't articulate it in those terms. They were fighting in tanks that were good enough, produced fast enough, replaced quickly enough to make losses temporary inconveniences rather than permanent setbacks. Every Sherman might have been inferior to its German counterpart, but there would always be another Sherman. There wouldn't always be another Panther. That asymmetry, more than any tactical innovation or strategic brilliance, is what won the armoured war in Europe. The tank every 5 minutes wasn't just an industrial achievement. It was a strategic weapon as decisive as any gun mounted on those tanks. Keller understood this from the beginning. The war would be won not by building better tanks, but by building more tanks faster than the enemy could destroy them. His illegal shift system, his relentless optimization, his willingness to push machinery and workers to their limits, all of it served that single objective. Overwhelm through production, drown the enemy in American industrial capacity, make the mathematics of attrition so lopsided that tactical excellence becomes strategically irrelevant. The workers who made this possible never fully grasped their historical significance. They were ordinary people, doing jobs they'd been told were important. They followed procedures, maintained quality standards, and went home exhausted. They didn't know they were rewriting the rules of industrial production. They didn't know their methods would influence manufacturing for the next century. They didn't know that distant historians would study their suggestion box ideas and shift rotation schedules. They knew only that tanks needed building and they'd been asked to build them. And build them they did. One tank every 5 minutes, rolling off the line with mechanical certainty while the world burned around them. 22,000 tanks from a single factory, enough armor to equip multiple army groups, enough steel to decide the fate of nations. All of it produced by people who'd never imagined themselves as anything other than ordinary. Citizens doing extraordinary work because their country needed them to. That might be the most American story of the entire war. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.